Okay, so it's fine that it thinks I'm muted. Okay, so we're going to continue with something that I would have liked to get to last time on Wednesday, but we didn't have time to. This is the last topic that we're going to talk about that involves wave optics. So we're going to talk about polarization again, but this time by reflection. So we've talked about how you can polarize with polarizers, but there's another way that we can produce polarization, and that's by using a particular type of reflection. So if so we know that light typically has a polarization, right? So the question then, a reasonable question would be to ask, well, sorry, light can have a polarization. So a reasonable question to ask would be, if polarized light bounces off of a surface, what determines the polarization of the returning light? Polarized light. Now, you might say, well, it's just the same, but what if it can't be? Now, and I'll draw a diagram in a minute or in a little bit that indicates that it can't be. But the key idea is, like, let's say you have polarized light that's coming in at, say, a 45-degree angle. And let's say it's polarized this way, right? So the law of reflection would say that the light wave would bounce back at a 45-degree angle. So it can't be polarized in the same direction because light is a transverse wave. It would have to be polarized, like, say, that way. So so this is something that actually is not an easy thing to answer. And so in order to understand it, we have to determine, or we have to understand what actually causes reflections to begin with. So it turns out that what causes reflections and what determines the polarization of light is the way, is the electrons in a substance vibrating back and forth. So a light wave consists of an electric and a magnetic wave oscillating in tandem. And as you guys will learn in 9C, an electric wave, or rather any electric field, influences charged particles. And in particular, electrons being charged particles and being very small, so they're easy to move around. When a light wave hits or passes by an electron, it makes the electron wiggle back and forth. And so the direction that God, my throat. Sorry. The direction that electron oscillates in determines the direction of the polarization of the re-emitted light, because the electron oscillates. By oscillating, it re-emits light, and the direction that the electron was oscillating in determines the polarization of the re-emitted light. Whether that emitted light is re-emitted as a reflection or as a transmission, that's a separate question, but the direction of that oscillation does determine the direction of that re-emitted light. That's certainly true. So then the question is how do we combine that feature, like that fact, with what we know about angles and so on, right? So, like, if a light wave comes in at a certain angle, how will that affect the direction that the electron oscillates in, right? That's a question that we in principle can answer, and unfortunately, it's a little bit beyond the scope of this class. It requires E&M. It actually requires, like, upper division level E&M, basically, maybe even grad level. It's not an easy problem. Like, it's doable. Like, we know how to do it, but it's not easy. But we can kind of abstract away from this notion of, oh, electric fields oscillating make electrons wiggle, and then those electrons wiggle and they oscillate more electric fields, by just kind of putting all of that stuff that happens right at the boundary of the interface. We put all of that into a black box, and we call it a boundary condition. So a boundary condition is basically a set of conditions. Like, these are like conditions or constraints on various things in some system. In this case, it's a constraint on the electric field. Boundary conditions basically tell us how something on one side of an interface should be related to something on the other side of the interface. So, for example, how should the electric field that's coming in how should the electric field that's coming in and bouncing off be related to the electric field that passes through? Boundary conditions tell us how those things should be related. And so in particular, there's a certain principle, I suppose, or a notion in physics that shows up frequently, and that's that boundary conditions should be continuous. So there's a sense of that things shouldn't abruptly change as you cross an interface. This is a notion. This is a mathematical notion, and if you take higher math classes, you'll run into this. But the basic gist is that like the electric field shouldn't go from like something to like nothing, or something to something completely different instantly, right? That's sort of a reasonable physical notion too. Like things shouldn't just jump, things should change smoothly. And we see that, you know, with regards to acceleration, like things don't go from 0 velocity to 5 meters per second in some direction. In the real world, things accelerate, and the speed or the velocity changes smoothly. So we want that kind of smooth change when it comes to the boundary conditions too. And so what we can do is we can actually leverage that fact to determine how how the polarization of these electromagnetic waves, the light waves, we can leverage this fact of continuous boundary conditions to determine how much of the wave reflects, how much of the wave passes through given a particular polarization. So what we're going to do is we're going to consider a case. We're going to consider the simplest case, where the incident wave to an interface, the incident light is polarized in the plane of incidence. And so let me just draw a picture. It's basically the same as the one that I drew above. Let me draw it in a little bit more detail. So you have your interface, right? You have your perpendicular. If you have a light wave that comes in, let me draw it in like red. If you have a light wave that comes in, it could have a whole bunch of polarizations, right? We know that a light wave is a transverse, is a transversely polarized type of wave. So we know that the polarization could be this way, but it could also be like into and out of the screen, right? As long as it's perpendicular to the direction of motion, it can be any of those. We're going to consider the case where the wave is polarized in the plane of incidence. And so what that means, what in the plane of incidence means, is that the polarization lies in this plane that we've drawn. So if you draw, so you know, if you take two lines, you can draw a plane between them. We just want that the direction of polarization is also on that plane. And so that would be rather than it going in and out of the plane, in and out of the screen. And this is the easiest one to draw, and it's the easiest one to justify. So this is the one that we're going to start with. And so we're going to call the angle that the incident beam or the incident light wave enters the interface, we're going to call that theta sub I for incident, and we're going to use theta sub R for the reflected angle and theta sub T for the transmitted angle. So the boundary conditions, and I'm not going to tell you where these came from. They take more than what you guys have to derive. But the boundary conditions, or the continuity of boundary conditions for this particular case where the wave is polarized in this particular way, are the following. So there's two of them. The first one is that the amplitude of the oscillation, E sub I, remember the amplitude is measured as the electric field, so like E plays the role of A here, it's the amplitude of the oscillation, times cosine of theta sub I, that's the angle of incidence. This should be equal to the amplitude of the reflected wave times cosine of the reflected angle, theta sub R, plus the amplitude of the transmitted wave times the cosine of the angle of the transmitted wave. That just is one of the equations that shows up if you go through all the work and do this continuity boundary conditions. The second one, oh, and by the way, we're going to call this n sub I and n sub T. So it's the transmitted, so n sub T is the transmitted index of refraction, and n sub I is the incident angle of refraction. It's the incident index of refraction. It is the index of refraction that the light starts in. A second boundary condition also arises. This one's basically a result of energy conservation. And it says that n sub I times E sub I plus E sub R, this is basically the total amplitude on the incident side of the interface, should be equal to roughly the amplitude on the other side, on the transmitted side, and they're modified by this factor of the index of refraction on either side. Now, these two equations, they just are true for and I mean, okay, there's a caveat that the material that the light is passing through has to be non-magnetic, but assuming the material is non-magnetic, which is way beyond the scope of this class, and the light is polarized in the plane of incidence, then you get that these two boundary conditions must be true. They are just facts of nature. Now, we can also write down two more things that just come from things we already know. From the law of reflection, we have that the reflected angle is the same as the incident angle. E is the magnitude of the electric field. Let me write that down. Sorry, it's the amplitude of the electric field. Because this is an oscillation, right? So it kind of plays the role of A in like an oscillation. Let me put this. E plays the role of amplitude. So it's basically the amplitude of the wave. So from the law of reflection, we have that theta sub I should be equal to theta sub r. That just says that the incident angle should be same as the reflected angle. If it comes in at 45 degrees, it'll go out at 45 degrees. If it comes in at 20 degrees, it'll go out at 20 degrees, right? And then also from Snell's law, we have that n sub I sine theta sub I should be equal to n sub t sine theta sub t. Now, we have four equations here. We have two up here, and we have two here that relate our variables, our 6 variables. We have the 3 amplitudes, the amplitude of each, the incident, reflected, and transmitted wave. And then we also have 3 angles, but we only have 4 variables, so we can't actually solve for anything yet. But that's kind of good, because we expect these things to be able to change depending on, what the index of refraction is, or what the what angle you come in with, or how much is reflected, or whatever. All of these things should be like related to each other, but this just tells us how they're related to each other. So, if we want to be able to solve for something, we need to be able to fix 2 more things. Now, the incident amplitude, we can just fix. Just don't treat it as a variable. Just treat it as the incident amplitude. So if you double the incident amplitude, all of the other amplitudes will double. So we don't really want to treat that as a variable. We just want to write the other amplitudes, if we wanted to solve for something, in terms of some multiple of the incident amplitude. So like, for example, you might say if the incident amplitude is this much, the reflected amplitude will be half that much, or 2/3 that much, or 0.19 times that much, or whatever. Basically, we want to just treat it as a constant that the other amplitudes are related to. Because, you can always just turn up the brightness of your light source or turn down the brightness of your light source, right? So that reduces us to 5 variables. Basically, we might want to solve for any of the angles, or E sub r and E sub t, in terms of the indices of refraction and the initial, and the incident amplitude, incident E. So we need basically one more equation if we want to be able to solve this system. But that's good, because it means that we can extract a lot of different scenarios here. We can extract, for example, let me write this down. We need one more equation. I'm going to put equation in quotes because we're not actually going to use a very complicated equation to do this, because this should describe any type of incident wave and any type of reflection. And we already know that there's going to be at least 2 types, or at least 2 different answers depending on what you choose. For example, if your incident wave is coming in at a really shallow angle and you're in a slow medium like glass and you're going to a fast medium like air, there should be total internal reflection, right? So for example, we could just pick the constraint. If we set the reflected light to be equal to the incident light, i.e. if we specified that we wanted to find the angle where all of the incident amplitude becomes reflected amplitude, and thus none of it would become transmitted, then we would find that the incident angle becomes magically, by solving this system of 5 equations and 5 variables, it becomes the critical angle for total internal reflection. So by specifying another constraint that the reflected light was equal in magnitude to the transmitted light, that was enough information. It gave us one more equation. It gave it basically 5 equations, 5 variables to solve for one of the angles. And this angle happens to work out to be the same angle that you would get that we derived using Snell's law for total internal reflection. Now, there's one more thing that we can get that's interesting. So we can get total internal reflection from these equations, fine, but we can get something more. We can also get, so that's when there's no transmission and 100% of the light is reflected. But we can also get 100% transmission and no reflection. And this doesn't involve interference, right? This isn't like a thin film interference where you have like where you have destructive interference. It's just the polarization and the boundary conditions just work out such that in order for everything to be continuous, you can't have any light reflected. And so the way that we do this is we just choose our second or our next constraint equation to just be that the reflected light has 0 amplitude. If the reflected light has 0 amplitude, what does that tell us about things like the angle of incidence and things like that? Well, if we do that, what we find after doing, a whole bunch of algebra, we find that the angle of incidence should be equal to the arctangent of the transmission index of refraction divided by the incident index of refraction. And this is given the name of theta sub b. It's called Brewster's angle, named after a guy who presumably loved brewing. No, I actually think that's a joke. I think his last name was just Brewster. So basically, this is a particular angle that if you shine light that's polarized in the plane of reflection or in the plane of incidence, if you shine it at just the right angle, then none of the light will reflect and all of it will transmit. So what does this look like? Like if we were to draw a picture? Well, we can draw our interface. Sorry, I can't draw a straight line. Okay, that'll have to do. We have our incident light. Let's call this angle Brewster's angle. So that's theta sub b, Brewster's angle. In this case, it has to be polarized in the plane of incidence. So I'm just going to draw the polarization arrows here, because this result only applies for this polarization angle, by the way. And then from the law of reflection, we would find that the light that reflected should also come off at Brewster's angle. But, and I'm going to draw this as a dotted line because it works out that actually no light comes out that way. And we can give a physical explanation as to why. So when light comes in at Brewster's angle, the light that bends out, or the light that comes out, or is transmitted rather, bends, that's not the right angle. There we go, bends down. And so again, because light is transversely polarized, the polarization direction would be, it's still in the plane of polarization or in the plane of incidence, but now it's in a different direction. And note that in order for there to be continuous, or in order for these continuous boundary conditions to be satisfied, this ray or that beam of light, that wave, would have to have polarization that's in the same direction as the transmitted light. It would have to have polarization that points this way, but it can't, because light is not light is a transversely polarized wave, which means that there just can't be any of that light. To say it another way, if the reflected light and the transmitted light would be at 90-degree angles relative to each other, if they would be at 90-degree angles relative to each other, then none of the light can be transmitted, because if it were to be transmitted, its polarization would have to be in the direction of propagation. But we already know that light has to have a polarization that's perpendicular to the direction of propagation. So what that means is just none of the light is, that there is no light that's propagated in that direction. By the way, like I said, this is only true for light that starts off for the incident light is starting off polarized in the plane of incidence. When the light is not polarized in the plane of incidence, when it's just in and out of the screen, for example, then you can always get transmission. There's no Brewster's angle equivalent. And that's because there's no angle that you can make between these that will not allow you to have polarization coming out. And that's just because, well, the polarization of the transmitted light would also be into and out of the screen. And so the polarization of the reflected light would also be into and out of the screen. And that's still perpendicular to the direction of motion. So the point here is that if you shoot polarized light that's polarized in the plane of incidence, there's a particular angle that if you shoot it at, none of that polarized light will make it out. All of it will be transmitted. So why do we care? Well, what if the incoming light is unpolarized, meaning it's just mixed, right? Like from the sun or from a light bulb. So if the incoming light, or if the incident light rather, if the incident light is unpolarized, why is the polarization of the transmitted wave specifically like that? It's beyond the scope of this class, but that is the direction that it would be in. I mean, we know that it has to be perpendicular to the direction of travel. And we also know that it should be in the same plane as the original polarization plane. The question then is why is it that the transmitted or that the reflected light has to have the same polarization? And that's a question that we just can't answer with what I've told you. But there is an answer for that, and it's related to these continuous boundary conditions. But that's the best I can do. And Brewster's angle is a very strange phenomenon. Honestly, I was thinking of not even including it in the curriculum because it's very bizarre. Anyway, so if the incident light is unpolarized, like the sun, like whatever, then at Brewster's angle, all of the light that let me not try to talk faster than I write. All of the reflected light must be polarized perpendicular to the plane of incidence. So if you have unpolarized light, if you have light that's polarized in the plane of incidence, then none of it gets reflected. But unpolarized light is just a mix of all the polarizations. So if you have unpolarized light coming in and none of the polarizations that are in the plane of incidence are reflected, then the only ones that do get reflected are already polarized, and they're polarized into and out of the screen, perpendicular to the plane of incidence. So we can apply this to make useful things. Polarized sunglasses can reduce glare. How does this work? Well, I'm going to draw a very rough picture. Here is the sun, and then let's say that you have a lake that the sun is going to bounce light off of, a lake. And let's say that there's you, LL Cool J, wearing your cool polarized sunglasses, right? Well, the polarized sunglasses are vertically polarized up and down. Now, when the light comes in, if it comes in at precisely Brewster's angle, well, the light that's reflected, okay, that's a terrible drawing. Let me draw the sun lower. There. Precisely Brewster's angle, then the light that reflects back to your face, this has to be polarized horizontally. i.e. the reflection off of the surface of the water would be polarized horizontally because the light that's polarized in the other direction all got transmitted through the lake because it came in at Brewster's angle. So this can reduce glare significantly, reduce reflections off of surfaces. And obviously, even if your angle is not exactly Brewster's angle, the amount that gets reflected is very small if you're just a few degrees off of Brewster's angle. And the amount that gets reflected will increase as you go further and further away from Brewster's angle. So this will be good, but this is particularly good when the sun is low in the sky. We care about glare when it's bouncing off of when the sun is low in the sky, bouncing off of a surface and coming to our eyes. We don't care about glare when the sun is straight from the sun or straight down. We only care when it's relatively low. And it turns out that Brewster's angle for water, I actually don't know what the value is, but when Brewster's angle for water is, it's going to be relatively low. So we can actually use this phenomenon. So there's an example in the LibreText and in the OpenStax book that I suggest you take a look at. But that's going to be the end of wave optics. We're done with wave optics. We're done with polarization. I mean, everything's cumulative, so there might be stuff that you need to use later. But we're going to start talking about a new topic now. We are going to talk about geometric optics. Geometric optics make up chapter 4. So this is chapter 4 of the LibreText. The final exam will not be cumulative. It will just be on geometric optics and beyond. There might be, well, yeah, it's not a final exam. It's just another midterm. So at this point, we've done a whole bunch of hard work with wave optics and Huygens principle, and like we've established that we can actually use these notions of rays to try to figure out where things are. Like, remember in the pictures that I showed you where you had the spherical source and then it bounced off of something, and then we could draw a ray and get the law of reflection from there. So we did all of this hard work. Oh, and also Snell's law. Snell's law came from Huygens principle, but it just applies to rays. So we did all of this hard work. So we can just take all of that hard work involving Huygens principles and waves and all of that business, store it in the back of our heads, and now we can just work with rays to try to solve more complicated problems. Now, just as a word of caution, so the lines that I'm going to be drawing are basically just calculational tools. Like, they're just there to help visualize, and they don't always represent light actually traveling along the depicted line. This is not going to come up today, because today we're only going to be well, actually, no, it will come up today. This doesn't always come up, and often the rays or the lines do represent light actually traveling in that direction or along that line. However, there's going to be this notion of like virtual images or virtual rays that we're going to come up with, and then it's just what direction the rays appear to have been traveling from. So just keep that in mind. Not all of the rays that I'm going to draw will be actual light paths. I will do my best to draw the non-physical rays as like dotted lines, but that won't always happen. Now, let's think about what we can do with rays. So with rays, we can locate objects. We can locate objects, or rather where they appear to be. I'm going to underline objects because that's a technical word. Now, if there's nothing fancy, nothing optical going on like around, if you're just looking at something, then the object appears to be, or the object appears to be where the object actually is, right? That's just true. But once you start adding reflecting surfaces or like surfaces with different indices of refraction where the light bends, things start to change. So that's why we need to have this notion of where objects appear to be. So this apparent location and the apparent location is all, like, it's not only where it appears to be, but also what shape is it in and what size is the apparent, like, if you guys have been in fun houses, like if you have weird optical things happening, things will appear to have different shapes and sizes. So the properties of what the object, or the apparent properties of the object, make up a visual phenomenon known as an image. So the image is basically what the object appears to look like. So let's ask specifically, what is an image? So an image is defined as what we see, or what somebody would see, or what a camera would see. And so it makes up things like position, the position of where the object appears to be, the size of the size that the object appears to be, and the direction or orientation that the object appears to be in. And these aren't always the same as the actual size, shape, and orientation. Sorry, position, size, and orientation of the actual object. For example, if you guys have been to fun houses where you have those funny mirrors, you're clearly not as fat as those mirrors make you look, or you're not as skinny as those mirrors make you look. And so clearly the properties of the apparent object, the image, don't have to match those of the actual object or image. What determines whether those properties change or not depend on, or the thing that determines whether those properties change is the path and the way that the light gets from the object to the observer. So for example, if I'm looking at this pen, there's no optical funny business here. So the way that the light is getting to the observer, I have basically two cameras in my head, one here, one here. The light is, the source is emitting, or the object is emitting light rays in all different directions. You have light bouncing off of it in all different directions. Some of those will get to my eyes. So the top here, the top will bounce off light that goes this way and light that goes this way. And the bottom will also bounce off light that goes this way and light that goes this way, but it'll also bounce off light that goes every which way. So the way that we figure out where an object appears to be, that's an interesting question. I can answer it afterwards, after lecture. So stick around and I'll do my best to answer it. Right. So the, right, where was I? Yeah, the way that we determine where an object appears to be is basically, if you take two cameras, two or 5 or 100 observers, where do those rays appear to come from? So you could draw a line from your camera's eyes to the source. In this case, it's the object of that light. Now that light is happens to precisely combine at the tip of the pen, and so to me it looks like the tip of the pen is located at the tip of the pen. But if somehow I redirected the light while it was on its way from the tip of the pen to my eyes, it might look like it's in a different spot or it has a different size. And so that's why we need to worry about this difference between an image and an object, because you can put stuff in the way, think lenses, mirrors, and so on, that will change the path that light takes and thus change the apparent direction that that light originated from. So pictorially, we're going to represent most objects with arrows, or objects and images, actually. We represent objects and images with arrows. So the reason why we represent them with arrows is because they kind of encapsulate all we need to know. They encapsulate the size, so the height of the arrow is the size of the object. The direction of the arrow is the orientation of the object. If it's pointing up, then the object's pointing up. If it's pointing down, then it's, well, I mean, yeah, there are lenses in our eyes. So yes, everything you see is an image. It's just most of the time, the way we imagine, or the way that we perceive the world is like our eyes are evolved such that the images produced by our eyes match the object's actual properties. Because if that weren't good, if that weren't the case, then you would try to reach for something and you would miss, because your hand would go where the image is, not where the actual object is. But you guys can test, if you reach for something that you see, your hand goes to the place where it should go, right? So the direction represents the orientation, and then the horizontal position, so these arrows will be vertical. The horizontal position represents the location. So that's how we're going to represent these. And the reason, like you could actually draw pictures and like see how that picture changes shape, but this encapsulates most of the information that we care about. So the question then is, how does this work? So I kind of already demonstrated this with the pen, but pictorially, let's say that we have an object over here. And let's say that I put one eyeball, by the way, this is how eyeballs are drawn in geometric optics, don't ask me why. Put one eyeball there and one eyeball here. So we want to figure out, where do these rays appear to come from? So we know that light is going to bounce off of these rays. That's going to appear to come from every which way. But some of those rays will get to each of our cameras from different parts of the arrow. So in particular, we can just draw some rays. So the ray that comes from the top of the arrow will go that way. And there will also be a ray from the top of the arrow that goes this way. And also there will be another ray from the bottom of the arrow that goes to the top eyeball, and a ray from the bottom of the arrow that goes to the bottom eyeball or camera. And so what this tells us, yeah, that's true. So I mean, in a sense, yes, everything is an image and that nothing actually exists. But like we can functionally we can function under the idea that the images do represent reality, because if they didn't represent reality, because it's an untestable claim, basically. That's a question of qualia and it's a question of philosophy. Right. Sorry for the digression. So the way that we determine where an image is we basically ask, where do the light rays appear to converge? Like if you backtrace the light rays, where do they appear to come from? And we do that by having multiple eyes, multiple observers, and then we find the point of intersection. So the top, these eyeballs would see the top of the arrow appearing at the point of convergence, and they would see the bottom of the arrow appearing again at the point of convergence. So with no optical devices in the way that bend or angle the light rays in any particular way, the object appears precisely where the image appears precisely where the object is, because the image is what they see, and they see that the top of the arrow is at the top and the bottom of the arrow is at the bottom. Now, just to be clear, there's light coming in going in every direction, right? From every point, not just the top and bottom, but if you can just view the top and bottom, then everything in between will just be in between. And so we only have to draw a few rays to figure out where the apparent image is, right? Because as long as you can find a point of intersection, you're good. That's enough to tell you where a thing is. Now, so this is just to say that if an object appears or is viewed directly, then the properties of the image precisely match the properties of the source object, as demonstrated here. But we can do things fancier, and this is where things get complicated. So we've already seen reflectors. So let's talk about planar reflectors, also known as mirrors. So they're planar, meaning that they're flat, and they're reflectors, meaning that they reflect. So from the law of reflection, we already know that when light strikes a reflecting surface, it's going to bounce off at the same angle. Theta I equals theta R. So we can find where an image is geometrically. We can use geometry to find the image. Now, notice, by the way, that we have already actually figured out where the image is. We did this using Huygens principle. And let me just go back and see if I can show you the... No, you know what? I didn't actually draw it. I don't have it pulled up on the other screen. Let me pull it up really quick, just so you guys can remember. Here it is. Second property for the arrows was direction. So the point I'm getting, the thing I was trying to convey to you was this notion. So using the law of reflection, using Huygens principle, we get that somebody observing the reflected light views the reflected light as if it were coming from another source, as if it were coming from something on the other side of the mirror. So now we can do the same thing just with geometric optics, just by treating rays as lines and applying the law of reflection. So that's basically what we're going to do. So the picture here is you have your planar mirror, just drawn as a line, and then maybe you have your object. So I'm just going to draw a horizontal line. So we know that just from the object, just that way, then I have a reference point. We know that light that comes from the tip of this object is going to bounce back the exact same way. But let's not look at that. Let's look at something more interesting. What if we wanted to figure out where does the light appear to be that hits this eyeball up here? And for some reason, the eyelash is inside the eyeball. Don't ask me why. Well, we could draw some rays. So if I get this right, these rays are supposed to be, they're supposed to have the same angle, but I don't think I drew this right, so that's okay. So there'd be a ray there, and let's put another eyeball up here. Where does this one appear to come from? Well, like there. About there, maybe? And again, this is rough. Like you could do this with a protractor and it'd be a lot nicer. So these two eyeballs would see, well, the rays don't actually converge. Like the way you perceive rays is by imagining that they're traveling in a straight direction. So they don't converge on this side. So it actually doesn't appear that the object is on that side. Indeed, it appears that the object is, or that the tip of the arrow is, okay, yeah, so this is a bad drawing, but it should be somewhere like there. The tip of the arrow is there. And so it actually appears that the image is over here. And let me just do some quick erasing, just because I promised that I would do so. So the important point is that light doesn't actually travel, oh boy. Light doesn't actually travel behind the mirror, right? Like the mirror, like light just bounces off the mirror, but it appears as if the light travels behind the mirror. And by the way, you could do the same thing for the bottom part of the arrow as well, and you would find that the bottom part looks like it goes to the exact same place. Like you could just draw the lines as I did, but I'm not going to. So the point is that it appears as if these light rays come from the other side of the mirror. They don't actually, they come from, this object, but it appears that they come from the other side of the mirror. And this is why when you look in a mirror, it looks like an object is there, like there's another person on the other side of the mirror. Like that's why that looks that way. Because the object to your, like that mirror of you is indistinguishable to the way we perceive light, as if there was somebody actually identical to you on the other side of a hole in the wall, right? Like that's just how this works. Like the light that enters your eye is exactly the same. And that's why it appears that there is this. Now, this type of image is something that's called a virtual image. And we will talk about this probably on Wednesday. We probably won't get there today. But this is a real thing that happens. Like we observe things that in places where they shouldn't be able to be. Right, so this thing, here, if this is the object over here, then this arrow is the apparent source of the light, and thus it is the image. So here, unlike viewing an object directly, when you put a mirror in the way, the object and the image aren't in the same place anymore. They still have the same size and the same same orientation zone, but they're in different places. So just to summarize, to figure out where an image is, what you want to do is you want to view the rays from more than one location, i.e. more than one like eyeball or more than one camera, and then you trace the rays back until they intersect. Now they might intersect somewhere like actually where the object is. They might intersect somewhere else, or they might not even intersect anywhere at all. And so you have to trace them virtually through the object that you're imagining, and that will tell you where the image is. Like I said, in this case, we would find an image of equal size and at the same orientation. And in fact, this distance should match this distance. I didn't draw it great, so it doesn't, but they should match this. They should have the same distance. Now, this is great. And for simple cases like the planar reflector, and yeah, for simple cases like the planar reflector, it's actually enough to just draw pictures and you can answer questions like, where does the image appear to be? But for more complicated systems, and like, I wear glasses, so like I need this math to be well understood, we need to attach some math to the process of locating images. And remember, geometry is just a type of math, so it's all the same thing. So, and when I say this process, I mean the process of locating where images are. So first, like as with most things in physics, you kind of want to establish a coordinate system. So we're going to put x, the horizontal axis, we're going to say that x is equal to 0 at the position of the mirror or the lens, or whatever optical device. So like x would be equal to 0 here. It's a horizontal axis. X is equal to 0 where that optical device is. And we call the midpoint, so like this point, we might call that the origin. So you have two axes. One is the horizontal axis, also known as the optical axis. The optical axis passes through the middle of your optical device, and then you have your vertical axis. But don't worry about the optical axis just yet. So the point is that this position, x equals 0, or this horizontal position, this is the point from which all other locations are measured. So we can write positions in terms of distances, right? You can say, oh, you're 5 meters to the right of the origin, or to the right of x equals 0. That would correspond with like x equals 5 meters or whatever. But we don't want to quite do that. We don't want to just say positive is to the right and negative is to the left, because things can get a little bit more complicated. That's why I put everything in quotes here, because it's not precisely a normal coordinate system like you're used to. So the next thing to consider is, what about positive and negative? I said that we're not just going to say to the right is positive and to the left is negative. And the reason we do that is because we want our math to work out to give us simple formulas that unify. So we will end up with the same formula for a lot of different cases. And so in order to do that, we need to introduce this notion of sign conventions. Sign conventions. So sign conventions basically tell us when is a variable positive and when is it negative. So all of the geometry that we're going to do will typically just get us absolute values. It'll get us this distance is this much times that distance, but distances are positive, whereas we want to be able to distinguish, say, to the left and to the right of the x-axis, or of x equals 0. So we need a notion of positive and negative. And so we just need to come up with some convention that makes our formulas work out. And it turns out that there's a well-defined set of sign conventions that works out nicely. So I'm going to draw a table, and this table is going to continue to be expanded upon for the remainder of our discussion on geometric objects, or geometric optics. So I'm going to tell you what the object is, what the mathematical symbol is that we associate to it. Like, do we want to call the size of the object h for height, or something like that? When that quantity is positive, and when that quantity is negative. So the first object would be, or the first thing to put in our sign convention is the object distance. So how far is the object from this x equals 0 point? So in this case, that is, we're asking about that distance there. So the symbol that we attach to that is s, just a regular old s. And we say that that distance is positive when the object is on the incoming side. Now I'm going to explain what the incoming side means in a minute, but just bear with me for a minute. We say that it's negative when the object is not on the incoming side, or the object is on the other side. Okay, that's what we decide. Like, that's the sign convention that we choose. Again, this is a convention, but it's a convention that everybody uses, so I'd stick with it. The other quantity that we would want to describe is the image distance. How far is the image from this central point? Well, it's some distance away. In this case, it's the same distance, but it's on a different side. So we need to convey that using sign conventions. The symbol we use is s prime, and we say it's positive when the image is on the outgoing side. And it's negative when the image is on the other side. We say it's negative when it's not positive, basically, which is to say if the image is not on the outgoing side, then it's negative, and if the image is on the outgoing side, then it's positive. So let me just summarize really quick what incoming, God, I really need to work on my posture. Let me explain what incoming and outgoing sides are. So by the way, those are the first two variables that we're going to introduce, and we will continue adding to this table as time goes on. So the incoming side, what that means is it's the side that light is on, this, like the side of the optical device, the left or the right in this example, the side that light is on before it changes direction. Another way to view this is the side that the light is on when the rays are pointing towards the origin. So when the rays are going this way, that's the incoming side. Alternatively, the outgoing side is the side light is on after it changes direction. So here we have two sides. We have the incoming side, which is before it changes direction. So it was traveling. So that means that this side is our incoming side. And then after the light changes direction, so at this point it changes direction and then it goes this way. Well, now the light is still on the same side. So actually, this side is also our outgoing direction. So in the case of a planar mirror, the incoming and outgoing directions are the same. That won't always be the case. For lenses, when light travels through them, the incoming and outgoing sides are on opposite sides. But for mirrors, that tends to be on the same side. Now, yeah. So it depends on the optical device, which is incoming and which is outgoing. But the notion that S or S prime is positive or negative, depending on the incoming or outgoing sides, that will always be the same. And the reason why we choose this is because then it can help us unify both lenses and mirrors, and because those are going to be related. So let me just give a quick example of this example of the, actually, let me just grab this. So the idea here is now we can attribute variables to the object's positions, so, or to the thing's positions. So this distance here, that distance is S. This distance here is S prime. So in this case, from our sign conventions, well, let's look. So when is S positive? S is positive when the object is on the incoming side. Well, the object is on the incoming side. So in this case, we have that S is positive. We also have that, well, from our sign convention, S prime is positive when the image is on the outgoing side. But here, the outgoing side is over here and our image is on the right. So here, our image is not on the outgoing side. So there, S prime is negative. Those are according to our sign conventions. So really, these might be better measured as like absolute values of S, but nobody ever writes that. So just keep in mind that that's what people actually are referring to. And so you can work out the geometry. It's actually really straightforward in this case for a planar mirror. That for a plane reflector, we have a formula relating S and S prime. It is just that S, or S prime, is equal to negative S. And that's our formula for planar reflectors, for mirrors. The object, if you are 5 meters in front of your mirror, the other you appears to be 5 meters behind the mirror. And this tells us both information about where the object or where the image is and how far away it is. Sorry, where it is relative to the mirror, whether it's on the one side or the other, and how far away it is. We'll get into things like distance in a minute, or height in a minute, but we're not there yet. Okay, so the next thing to talk about is another type of optical device, and that is the plane reflector. Sorry, plane refractor. Causes refraction. Remember, Snell's law is the result of refraction. So, you know, what we're going to basically end up doing is we're going to look at different optical devices that you can produce. An optical device, by the way, is any device that bends light. Can you explain the position of the light source in relation to the sign convention? When you say position of the light source, do you mean the object, or do you mean like what's actually producing light? Like if there's a light bulb in the room. So it doesn't actually matter, because as far as we're concerned, every object emits light in every direction. And the reason for that is that, like, in a well-lit room, there's light hitting the pen from every direction, because it's bouncing off of the walls and it's hitting it in all sorts of directions. And then the light, because, you know, the surface of my pen is not perfectly smooth, it doesn't bounce off perfectly according to the law of reflection. It bounces off, you know, mostly in the law of reflection, then a little bit in other directions. That's called diffuse reflections. So the point is that this pen basically appears to reflect light in every direction from every point on it. That is, it just appears to provide its own light source. We know that if I turned off all the lights, this wouldn't still be glowing, but we can treat it as if it did for the sake of geometric optics. Right. So we can also treat, so what I was saying is that what we're going to do is we're going to analyze a whole bunch of different optical devices. These are devices that change the direction that light travels in, and just see what they do to our light rays. So we've already seen how reflectors can change what they do. One thing that we've also talked about is Snell's law, refraction. We know that if you enter an interface, the light is going to bend. So we're going to ignore the reflection part of Snell's law because we've already covered that with the planar reflector. We can now study the redirection of light by, oops. One sec, sorry. Okay, it's already at 100. We can study the redirection of light with refraction. I.e. Snell's law. So we're going to study what happens when you have light bending as a result of changing medium. So should I draw this or should I just show you? No, I'll draw this. So here's our, let's say we have a medium here. We have N1 on one side, we have N2 on the other. And let's say that N1 is smaller than or is greater than N2, just for the sake of drawing a picture. And let's say that we have an object, say over here. And by the way, this is assumed to be like, you know, taking up the whole area. On one side of the universe, you have N1, and on the other side, you have N2. And let's say that we have an eyeball, say, here, and an eyeball maybe I don't know, like here. So we know that some light will come from our source, and when it encounters the surface perpendicular to the surface, it'll just go straight. So wanted to, let me draw it in red, actually. Oh boy. Okay, there we go. So it just goes right through, ends up at our eyeball. But what about light that doesn't enter? Well, some of it is going to come in an angle. And we know that when a light source goes from a slow medium to a fast medium, that is from a high index of refraction to a low index of refraction, it bends outwards. I didn't draw that perfectly properly. And so what actually appears to happen is that these two eyeballs do, oh, I should have drawn that in green, sorry. For those of you who are red-green colorblind, by the way, I'm very sorry. So the light actually doesn't appear to come from where it actually comes from. Instead, it appears to come from this location. That's where the object appears to be. And then you could do the same thing for the bottom, and you'd find that the object looks like this. Same size, just in a different place. No, mirages are well, there's a bunch of different types of mirages, but there are definitely mirages that are a result of actual optical phenomena doing funny things. Yeah. Now, so that's where the image would appear to be. So we have an object and we have an image. And now they're in different places because the light bent. Now, I have to be careful here. Just like with the reflection, not all of the refracted rays. Oh, no, actually, this is a separate thing. So because the sine, if you were to plot the sine function, like this, sine is it's not a linear function, right? And because it's not a linear function, obviously, it's actually not the case that all of the refracted rays will intersect at the same point. Some of them will, they'll intersect at some fuzzy point. Some of them will intersect here, some will intersect here, and so on, depending on the angle. And so as the angle gets bigger and bigger, as you go to more steeper and steeper angles, the place where it intersects will be at more and more different places. For example, because this index of refraction n1 is greater than n2, if you enter at a shallow enough angle, in fact, none of it will make it through. It'll just be totally internally reflected. So you can see that if it came in at just under that angle, it would basically bend straight outwards. And then, well, now it doesn't intersect at this right place. However, if we assume that that all of the angles are small, all of the angles in the problem are small, what does that mean physically? That would mean that, for example, that the object is small compared to the distance between the eyeballs and the interface and things like that. Basically, like imagine a penny at the bottom of a pool. Like when the angles are small, then we can use the small angle approximation, which is just that theta is approximately equal to sine of theta, which is approximately equal to tangent of theta. And if we make that assumption, then all of the points or all of the refracted rays will appear to converge at a single point. And so you can find a point of intersection of these rays. So that's the approximation we're going to make. We're going to make that the whole way through, if only because you can't really do geometric optics without it. Now, let's actually do some geometry on this picture. So with the small angle approximation, I'm going to get rid of these eyeballs because we don't actually need them, but I'm going to keep them there. So I'm going to draw I'm just going to draw a line horizontally here at this point of intersection. Actually, is that really what I want to do? Yeah, that's fine. I'm going to draw a horizontal line, just that way then we have something to reference angles off of. So we'll call this angle theta 1. We'll call this angle theta 2. Right? Like in principle, we can do that. Oh no, never mind. We won't call that angle theta 2. I'm sorry. We will call this angle theta 2. And the reason why we're doing this, by the way, is because this angle theta 2 will help us figure out where these objects are, or where the object and the images are, using some geometry. So this distance, that's s prime. That's the distance from the image to the origin. This distance, that's s. So we have theta 1, theta 2. We have s prime. And we can also find that these objects, just by definition, have to be at the same height because they intersected at a point of the same height. So this will be some distance, call it h. This will also be some height, call it h. I know that this is getting messy, but we have some geometry to do. Okay, so now we can just do some geometry. So from the small angle approximation, we have that sine of theta 1 is approximately equal to the tangent of theta 1. Now the tangent of theta 1, well, the tangent of theta 1 is equal to the opposite over the adjacent. So it's equal to h divided by s, right? Similarly, we have the sine of theta 2, because it is the same angle, like it's also that angle there. Sine of theta 2 approximately equal to the tangent of theta 2, which is equal to, well, it's the opposite, so it's h divided by the distance, s prime, h over s prime. And so we can apply Snell's law, which tells us how n1 sine of theta 1 equals n2 sine of theta 2, to get us to n1 times h over s should be equal to n2 times h over s prime. And so directly from there, the h's cancel, and we end up with that s prime is equal to n2 divided by n1 times s. Great. So this tells us where that object is just from using geometry. This is why this is called geometric optics, by the way, because you can do this with like protractors and stuff. Now we just have to be careful. We want to use the same sign convention that we developed above. So what is the sign of s? Is s positive or negative? Well, the incoming side is the side of the interface before the rays change directions. So before the rays change direction, the light is on this side. After the rays change direction, it's on this side because the light bends at the interface. So in this case, the object is positive. The object is on the incoming direction, or the incoming side. So S is positive. What about S prime? Well, in this case, the image is not on the outgoing side. The outgoing side is the opposite side because it's the side where the light ends up. It's the side after the light bends or changes direction. So according to our sign conventions up here, S prime is negative when the image is not on the outgoing side. So S prime is negative. So remember, this equation is just about magnitudes. It's just about absolute values. So if we want the actual equation, we can combine these, combine a measurement or an equation about magnitudes and statements about sign to get the formula for the plane reflector. Sorry, plane refractor. For the plane refractor, we have that S prime, the location of the image, is negative n2 over n1 times S. And we just found that using the small angle approximation and some geometry. Now, I haven't mentioned this yet. Actually, I may have mentioned it. Maybe. So the horizontal line that splits the optical device in half. So if you have like a lens, right? A lens is another example of an optical device. The line that splits it in half, so that would be, in this case, maybe it would be this dotted line that I drew. Or in the case of the plane, it would be the planar mirror. It would be this dotted line. The line that splits the optical axis in half, sorry, the horizontal line, sorry. That splits the optical device in half. Is called the optical axis. Now, it doesn't really matter where the optical axis is for planar optics, for a plane reflector or a plane refractor, because it's the same regardless of whether you are above or below the optical axis. But for once your optics start to become curved, like in lenses and curved mirrors, then it gets a little bit trickier. So we have to introduce this notion of the optical axis, and we usually orient our objects perpendicular to the optical axis. Like in the above drawings, they were all perpendicular to the optical axis. And we often place the bottom of the arrow on the optical axis. So I didn't do that above, but I will try to do that going forward. So the picture would be something like you have your mirror, you have your optical axis, and then you'd have your object here. So the bottom of the arrow is on the optical axis. And the reason why we do that is because it means that the bottom of the object is always in the same place. So we only need to analyze where the top of the object is. Okay. I guess I didn't need to erase that. Sorry about that. Let me put it back. There we go. Right. Okay. So that tells us, for the simplest case, where an object is. Planar reflection, planar refractor, relatively simple geometry. Now, before we move on to start talking about more complicated things, in all of the cases that we've discussed so far, the object appears the same size, or the image and the object have the same size. But that won't always be the case. So we need to talk a little bit about magnification. So this is section 4.2. For those of you who want to take a look at the LibreText, I would recommend it. There's some good diagrams there. So we can measure, like, remember what I said about an image before. An image isn't just about where the object appears to be. It's also how big the object appears to be. So we can measure how much an object shrinks or grows. Sorry, how much an image shrinks or grows vertically. with a quantity called lateral magnification. Lateral meaning perpendicular to something. In this case, it's perpendicular to the optical axis. So there is such a thing as longitudinal magnification. I'm not really going to talk about it much, but there is a section on it in the textbook, so I suggest you take a look because it's interesting. Right. So lateral magnification is just it's just a number. It tells you, does the object shrink? Does the object grow? Does it flip? And so on. So let's say an object has height y. And an image with height y prime. By the way, I don't think I said this, and I feel like I didn't say this because I thought it was obvious, but it might not be because this is new for a lot of you. It'll actually be new for most of you. What we're doing here is we're depicting like an optical setup viewed from the side, right? I can't believe I went this far without saying that, but like the idea is like you have a thing, you have one thing here, and then you have like maybe like a mirror or like a boundary of water or something. And then it's maybe you have an image appearing over here or an image appearing here or whatever. But the point is you're viewing it from the side. We're trying to picture what's happening from the side so we can draw these. So the optical axis, like if you were to look down, like if you were looking at a mirror, you're not viewing it from the side. You're viewing it along the optical axis. So yeah, just wanted to make sure that that's clear. Sorry about that. Right. So if an object has height y, and the image has height y prime, then we can define m, the lateral magnification, like a 3-bar equal sign means define. Also, you may have seen this, actually, let me use a different one. Let me use a different notation. Colon equals means it's defined to be. You guys, those of you who are programmers might be familiar with this. It's defined to be y prime divided by y. So basically, it's just the ratio of the heights. So if the magnitude of m is greater than 1, then the image grows. Let me write that a little bit better. If the magnitude is less than 1, then the image shrinks. The image is smaller than the object, and vice versa. Now, for a mirror, and hopefully this matches with your intuition, y prime is equal to y, which just implies that m is equal to 1, and so the image isn't stretched or shrunk when you look in a mirror, a regular old mirror. It just moved. And so that should agree with your intuition. Like, it doesn't look like you're 8 feet tall when you look in a mirror, right? Yeah, if the magnitude of m is equal to 1, then the image is the same. But what about for a refractor? Like, a refractor, by the way, would be like the surface of a swimming pool. Like, if you throw something into a swimming pool, how does it, yeah, unless you're 8 feet tall. If you throw a penny into a swimming pool, does the penny look bigger or does it look smaller? Well, we have to be a little bit careful here. So for a refractor, it turns out that y prime is also equal to y. This is for a planar refractor, rather. And this takes some work. I mean, it's just an extension of the geometry that we did earlier. You just have to do it twice, basically, and then find a difference. We also have that y prime is equal to y, which says that the magnification of a planar refractor is 1. So why is it then, and you guys have all experienced this, I hope, objects look bigger underwater? Why is it that if you throw something, like if you throw a penny underwater, it looks bigger than it did before it was underwater? We can answer that question now. Now, to be clear, if you're in the water with it, then it's not going to look bigger. because there's no change in index of refraction. There's no actual like optical device. But if you're outside the water and you're looking at something in the water, that thing will look bigger. Like you guys should all be familiar with this. And the reason this happens is not because of lateral magnification. Lateral magnification actually just tells us how the image and the object, how their heights actually compare. There's another thing called angular magnification. Angular magnification is actually how we view the world. This tells us how much larger a thing looks. Not how much larger it is, but how much larger it looks. So an image has an actual size. You can treat an image almost like a real thing. It has a size. But that doesn't mean that it'll look, even if its size is the same as the object, it doesn't mean it'll look the same size. And the reason is because the angular magnification tells us how much of your field of view does an object take up. Like if I put this pen right next to my right eye and close my left eye, it takes up like a significant fraction of my field of view, right? Like maybe, okay, that's a bad example because it's very narrow. Wallet, right? If I take this wallet, put it right next to my eye, it takes up like 90% of my field of view. However, if I take the same size wallet, put it, 2.5, 3 feet away from me, well, now it takes up like 4% of my field of view. And so the point is that that's how we like when something looks big, it could also mean that it just looks close. So m sub theta is theta prime divided by theta. So going back to look at our refracting image, it's the ratio of these angles. And so clearly, for refraction, theta 2, at least in this case, when n1 is bigger than n2, theta 2 is bigger than theta 1. So theta 1, or theta and theta prime, describe how much space. Space in quotes, of course. Or field of view, for those gamers out there, the object or image takes up in our vision. So for a plane refractor, m equals 1, but s is greater than the magnitude of s prime. The image looks like it's the same size, but closer. And so what that means is it implies that theta prime, which is the theta associated with s prime, is greater than theta, which implies that m sub theta, the angular magnification, is greater than 1, which just says that it looks bigger, even though it's not bigger, it's just closer. I.e., the bottom of a swimming pool, if it's 8 feet away, if the swimming pool is actually 8 feet deep, the bottom of the swimming pool will not look like it's 8 feet away. It'll look like it's 6 feet or so. However many feet, it doesn't look like it's as deep. Not quite like a telescope. We'll get there, but we're not there yet. By the way, just as an aside, if the image is flipped upside down, which can happen, then y prime becomes 0. Sorry, not 0. Y prime becomes negative. And what that does is it lets us say that the magnification is negative. And we're going to see examples of this happening later. It doesn't happen in the case of planar reflectors or refractors, but it can actually. No, it doesn't. But it can happen for other situations that we'll see later. You can also, by the way, consider how objects stretch or shrink or flip along the horizontal axis, along the optical axis. So like, for example, if you are looking in like a sink full of water and you put a spoon down, viewed from above, the spoon is going to appear to change shape, right? Like like it'll appear to shrink or stretch or whatever. So you can also study that, and that's called longitudinal magnification. You can study how a reflector or a refractor affect longitudinal magnification. And there's a quick summary about that on the, oh, did I not write enough notes? No, I did. There's a quick summary of that on the, in the LibreText that I suggest you take a look at, and there's good examples, and that's something that you guys should be aware of. But it's not going to be, well, I don't want to say anything, but go take a look at that. It is in, so I'll just write this down. Longitudinal magnification. I don't want to spend lecture time on it. See section 4.2. Okay, so with those magnifications out of the way, those are the 3 types of magnifications that you can get. And really only the lateral magnification is the one that we're going to worry a whole lot about. We can fill in our sign conventions. So add to your table. I'm not going to rewrite the whole table because part of it's already there. So the next thing on our sign convention, so we have name, we have symbol, we have when it's positive, and we have when it's negative. So the name here is lateral magnification. The symbol, well, we already know that, it's M. And it's positive when the image is upright, when it's in the same direction as the, when it's oriented the same way as the object. And it's negative when the image is inverted. Okay, that's just another sign convention. It's useful to know. Yeah, I guess I'll start on the next bit. Does anybody have any quick questions like about this material before I continue? Take that as a no. So the next thing is, okay, so that tells us that basically covers all of it as far as planar reflectors and refractors go. They're really not that interesting because the sizes don't change. Things just move around. What does get interesting are spherical reflectors. Now, I don't actually know how far we'll get. I didn't prepare notes that finish this section, so we'll see. I might just run out of notes and then we'll be stuck. Spherical reflectors are covered in detail in section 4.3. I'm going to do my best to also cover them in detail, but a lot of this relies on good drawings, so my drawings might not be great. So a spherical reflector is basically the answer to the question, what if the reflector is not planar? Planar meaning shaped like a plane, i.e. flat. So what we're going to do, so we could, in principle, you could consider just arbitrarily curved mirrors. That's really hard, like really hard. That falls under the field of analytical geometry, which is like a research field. We're going to consider like the most simple non-planar case, which is partially spherical mirrors or partial spherical mirrors. So imagine that you had like, the idea here is imagine that you have a like a really, really shiny metal ball, shiny on the inside, shiny on the outside. Now like cut it somewhere. Now you have like part of a sphere that's effectively a mirror, right? And you could you could put an object near it, and then you can look in the mirror and it'll look like the object will look however it'll look. And then you could flip it around and you could do the same thing. So we're gonna, that's going to be the case that we consider. We're gonna first talk about concave mirrors. So concave mirrors are, and maybe you guys know this already, but a concave mirror, the way to remember this is it's like a cave. Like it's like you can go into it, so it's bent away from you. So the geometry of a concave mirror is the following. So I'm not even gonna draw any objects, I'm just drawing the geometry of the mirror. So you have your, terrible, I'm sorry. Nope, still bad. Nope, okay. One more try. Okay, that's pretty good. Okay, so here's our mirror. And typically, by the way, and this isn't always the case, but typically when we're doing optics, we put like the light source is on the left. Like the object is usually on the left and so on. So I'm going to draw a line that passes through the middle. Remember, the line that passes through the middle of our optical device is called the optical axis. So here, this is our optical axis. Here it matters because if you put it up here, the geometry would be different, right? So we want to put it through the middle. Erase, please. That's not what erase does. Okay, that's also not what erase does. Cool. Okay. Okay. So also, this is a part of a sphere. So a sphere has a center. So if you draw a perpendicular from the surface of the sphere, there will be a point that every point is equidistant from. This point also is known as the center. This is labeled C. It's a very round C. It's called the center of the mirror. The distance from the center of the mirror to the mirror is the radius, capital R. It's also known as the radius of curvature. This point here, where the optical axis intersects our mirror, that point is called the vertex of the mirror. So these notions are useful because they'll help us get the geometry right. So this is just what our geometry looks like, and then we would like put an object over here and see what happens. So a concave mirror has the center on the same side or on the initial side of the object. So like if your object is over here, this is the incoming side. And we'll actually talk about this. There will be a sign convention for R2, but we're not going to get there yet because I don't think we'll get there today. So to determine where images are given an object, like if I just put an object here, to determine where images are, we just use rays again. You just plop down a whole bunch of eyeballs, figure out where do the rays that come from those eyeballs, where do they come from? Or the rays that hit those eyeballs, where do they come from? Where do they appear to come from? And we would just use the law of reflection here, right? Like if a ray comes in straight onto the mirror like this, then it bounces back straight. If it comes in at an angle, then it bounces back at an angle. But because the surface is constantly, turning, it's a little bit harder to actually like work out what does the geometry do. And so we have to think a little bit, oh boy. Okay, no, it didn't close. So we have to, there's a little bit more work to do. So at the end of the day, we really want to derive S prime being the distance from the image to the vertex, really. So we have to be careful here because we want to write, just like in the previous examples for the planar reflector and refractor, we want to write S prime in terms of S, and then maybe some other things like other constants, indices of refraction, things like that. But how do we know where to measure S from, right? So we can measure S from here to here. That would be a shorter distance than if we measured S from here to here, right? So we need some consistent way to do this that makes sense. And similarly, S prime, where is S prime measured from? From the top, from the bottom? For the planar case, it didn't matter. So what we're going to do here is we're going to make another approximation. We're going to approximate the mirror as nearly flat. And the reason we will do that is because then it doesn't matter where you measure S or S prime from, whether it's the top or the bottom. It's going to curve sufficiently slowly that if you measure from the top or the bottom, it's basically the same result. But it's still going to have curvature. It just won't have very much curvature. And that'll let us make easier and better geometric assumptions. So by the way, this doesn't mean that we're just going to treat it like a regular old planar mirror. It still has curvature. All it means is that the height of the object is smaller, significantly so, than the radius of curvature. If the radius of curvature is really, really big, like if you have a really big mirror, then the height of, and like if your radius of curvature is 10 meters, say, and your object is, say, 2 centimeters tall, then as far as the object is concerned, whether you're measuring it from the top or the bottom doesn't really matter. So what this will let us do is it'll let us basically just treat this as if the mirror were just like a flat plane. It's technically curved a little bit, but we can draw it just as a flat plane, and that's what we're going to do. So let me draw a better picture. Come on, please erase. Okay, there we go. So let me draw a better picture. So you have your curve, you have your mirror. This time the radius of, or actually, let me draw it even less curved. Really large radius of curvature, right? Here's our optical axis. So we can just basically approximate our mirror. Oh, and I should probably, there we go. We can approximate our mirror as just this line, or that's what we're going to do. This, I'm going to double it up just so then you can tell which one I'm pointing to. This thick mirror, this is what we're going to use to treat our mirrors. This is our flat approximation of the spherical mirror. Now we still have to take into account that when you strike the mirror, you're striking at an angle, and the angle changes depending on where you're striking. But we can at least now handle this a little bit more easily. So if we have an object, say here, actually, let's just say you have an object that's just on the optical axis. So you just have a point. Well, so what's going to happen? It's going to touch the mirror at a point. It's going to bounce back. Now, what angle does it bounce back at? Well, that depends. It depends on the angle that it hit with. But maybe it bounces back at this angle. Just let's just say, oops. Like how to draw these will be made clear. There's a way to do this, but oh, and by the way, this actually, let me back up. There's actually a way to do this, right? If, say, this is the center, this point C is the center, well, we know that the angle should be the same angle on either side of that perpendicular line, because this is the perpendicular. So the angle should be roughly the same. It should be the same here as it is here. So this would mean that your eyeball over here would see the object as if it were coming from here. So here is an image. And the reason we know the image is there is because if you were to draw a horizontal line going straight to the center, it'll bounce back perfectly, right? Because you're hitting the image straight. So the image, even though the object appears to be to the left of the center, the image appears to be to the right of the center. So the image moves here. Now, there's also things that are going to happen, like the size of the image will change. And we'll talk about that, I guess, probably next time. But the point is that this is a way that you can determine where an image is by using geometry in the same way. Now, just as another caveat, like we said with the refractor, I don't want to say this. The location of the intersections will actually only approximately all intersect at a point. Like if I did this a whole bunch of times, they would very nearly cross at that point, but they wouldn't exactly cross at that point every time. And the reason for this is because the spherical approximation isn't a perfect one. Again, we're making another approximation. By the way, all these approximations are good in real life to good enough to get like glasses. But like if you need precision instruments made, like 1,000 times magnification microscopes and things like that, then you have to be a little bit more careful. And there's things like this phenomenon where you have not all of the rays actually intersecting at a point. This is called spherical aberration. Basically, it's the phenomenon where things don't quite line up because it's spherically shaped. If you wanted to do this ideally, you would actually have a parabola-shaped mirror, and then you wouldn't have any aberration. But the reason we use spherical mirrors in real life is because it's actually really hard to make parabola-shaped mirrors. And it's really easy to make parabola-shaped mirrors, or sorry, it's hard to make parabola-shaped mirrors, very easy to make spherically shaped mirrors. So that's what we work with. But to a good approximation, this is fine. So I guess on Wednesday, we will continue with actually solving for where this point of intersection is. For now, I'm going to end lecture. I do want to remind you of one thing. Grades are out for the midterm. These are raw grades, not curved grades. So I know it'll look low, but that's okay. These are not curved yet. What you need to do before tomorrow at noon is you need to go through and verify that, like, you need to look on Gradescope at your grades, or at your grade for the exam, and you need to check that it's been graded properly. You can, and if it hasn't, then you can submit a regrade request. If it has, then you're fine. Those are due tomorrow at noon. After those are due, I will have the TAs look at the regrade requests, whether either approve or deny them. And then I will do some statistics on the regraded results, and then release a curve. And those will be plugged into Canvas. So make sure you take a look at that. Like there'll be no exceptions. If it's afternoon, like you take the grade that you get. Like even if it was graded incorrectly, that's on you. All right, so I'm going to end lecture now. And I will open the floor to questions.